Hello, my name is Siddharth S. Ramaswamy and I'm from the Aerospace Department. And today I would like to explain the polymer composites for supercapacitor applications. To understand what a polymer does for a supercapacitor application, first we need to know what a supercapacitor is. A supercapacitor is also a high ultracapacitor with a very high capacitance value, much more than what a normal supercapacitor has. The ongoing climatic changes, global warming, depletion of fossil fuels, and the increment in the wastage of power resources have led us humans in search of a new and reliable source of such power. To cope up with such ever-growing need in storage of power resources, us humans have found different ways of generating and storing such enormous loads of power resources. Supercapacitor is one such invention made by humans in recent times to cope up with ever need in power resources. These supercapacitors are not only super reliable but also have the abilities to store 10 to 100 times more energy per unit volume than a normal traditional electrolytic capacitor. The ability of the supercapacitor to store such energy in large amounts and provide it for the usage in a more resourceful way than a traditional supercapacitor are made us realize how much of an important role it plays in the energy generation for the current generation of human beings. During the process of supercapacitor manufactures, supercapacitors are mainly used by activated carbon from coconut shell to make supercapacitor electrodes as it is cheap and suitable for mass production. The cost has dropped drastically in the past few years with the application of low-cost materials during the manufacture. Polymer sheet grown with the process of chemical deposition as high quality and least defects during the production of supercapacitors with the help of polymers. During the production of supercapacitors, graphene and polymers play an important role. Graphene nanosheets, which are produced also through chemical vapor deposition, require binding with the help of polymers. Among them, PVDF or polyvinylidene fluoride and PEFE polytetrafluoroethylene are majorly used. During the production of PVDF, the binding process has to be controlled carefully as a binding between graphene and polymers can be weak and cause adhesion issue. In addition to mixing and coating, vacuum filtration method can also be employed to form polymer supercapacitors. These conductive carbon materials are normally 20 to 50 Newton meters in size and are dispersed evenly onto the graphene material. Inactive materials were 90% reduced graphene and 10% of carbon black, and the active materials were mixed with PVDF with a ratio of 95:5, then coated onto nickel to form electrodes. The addition of carbon black does not change the overall morphology of the reduced PVDF electrode, but only increases the usage and the conductivity of the electrode. PVDF capacitors also help in high electrical conductivity of electrode and improve the capacity and cycle stability in the supercapacitor electrode. Some of the advantages of the PVDF capacitor is to act as a filler material to suppress the aggregation of graphene nanosheets, to improve the rate capacity and cycle stability of the supercapacitor electrode, and also to maintain high electrical conductivity of the electrode. And one other such polymers used during the production of supercapacitor is PTFE supercapacitors. PTFE is another polymer blinder which is used to blind with graphene. As we see in the picture of a polyfluoroethylene molecule, these molecules have more amount of fluorine atoms than the PDF supercapacitor. PDF is insulating and highly hydrophobic, and too much PDF could decrease the conductivity and binding capacity of the polymer. Also, the insufficient usage of PTFE could reduce the usage of capacitance and the conductivity of the polymer. But good wettability conditions can provide easier access for the electrolyte ions to enter the porous structure of the electrodes materials and thus achieve higher double layer capacitance. To increase the hydrophility of PTFE binder to some of the aqueous electrolyte, a tiny amount of polyvinyl pyrrolidine PVP depending on the chosen electrolyte, the graphene based supercapacitor can behave differently. PTFE as the binder to form a graphene-based supercapacitor and tested in both aqueous and organic electrolyte. It plays my major role in the storage of such power resources. One such other supercapacitor and have been used in the recent times is polyaniline supercapacitors. Polyaniline polymer is also being studied extensively in recent times due to its exceptional qualities. Polyaniline or PANI needs a proton to be conducting and properly charged and discharged. Thus, a protic solvent and acidic solution or a protic ionic liquid is required for the PANI to be used in the supercapacitor applications. The most common synthesis made of PANI are oxidative polymerization and electrochemical polymerization. Other methods can also be used to produce nanostructures PANI, such as interfacial polymerization, electrospinning, seeding polymerizations, templated polymerizations, and etc. Composites of PANI and graphene can be prepared by polymerization of aniline with graphene suspension in acidic solution. PANI composites are of 30 to 40 Newton meters thick and very few micrometers in size, which suggests a large specific area of these nanocomposites. One other such composite which are used during the process of manufacturing of supercapacitors are polypyrrole composite. Polypyrrole composite or PPY composite is also a polymer which is being used in the recent times. PPY was first demonstrated by Weiss in 1963. PPY is also a very attracting CP material for supercapacitor applications since the synthesis of this polymer is simple and it has both good conductivity and thermal stability. The pure PPY polymer has very different morphology compared to the PNI polymer. The PPY film, which contains submicron particles and later forms aggregated cauliflower-like structures with increasing polymerization charge to increase the film thickness. Such aggregated structure of the thick PPY film is not favorable for supercapacitor applications since they minimize the surface area and have the tendency to block the access of electrolyte ions. In addition, during the charge and discharge of cycles, these particular structures can easily collapse due to the stress caused by the volumetric change. Generally speaking, pure PPY film has inferior cycling performance as supercapacitors compared to a PANI polymer. Similar to PANI polymer, polymerization with graphene is preferred, and by doing this process with graphene, we can minimize the aggregation. One such polymer used during the recent times, similar to the PPY film, is the P-dot composites. P-dot composite or polyethylene dioxythiophene was first developed in the 1980s by a scientist named Bayer in Germany. P-dot can be prepared using standard oxidative chemical or electrochemical polymerization methods and has very high conductivity. P dot was first found insoluble, but later this solubility issue was circumvented by using a water-soluble polyelectrolyte, and now it has excellent cycling stability with over 80% capacitance retention over 70,000 cycles, unlike the PPY film. However, one disadvantage of the P dot supercapacitor is the large molecular weight, which leads to a low specific capacitance. In order to minimize the aggregation of graphene nanoparticles in the composite, similar in the PVDF polymerization method, can be used to form the graphene P dot composites. Now, the conclusion of usage of polymer in the application of supercapacitor is the emergence of polymer has played a major role in the development of the supercapacitors. The outstanding electrochemical properties and large surface area of the polymer help in paving way for the future developments of the supercapacitors. Also, with the development of such supercapacitors with the help of polymers, we also face quite a few problems in recent times. One of the main challenges is to find feasible way for the low-cost mass production of graphene or polymer supercapacitor electrodes without compromising the micro and nanostructures of polymers. Many studies have demonstrated the compatibility of large-scale coating or roll-to-roll manufacture capability of graphene polymer supercapacitor electrodes. However, there is still a need to have rational design and porous structures inside the supercapacitor electrodes for the functioning of the supercapacitors. Thank you.